Good. Good. So let's have a little look at this. So, axes, radius against energy.
I want to move it down a bit.
Okay, sorry. There you go. Alright, so this equation was, so basically our effective potential, VFF as a function of R, was equal to L squared over 2R squared minus GM over R. Okay, let's do the easy bits first. As R goes to infinity, what does this expression become?
Zero.
It's tiny, it's 0, right? Both the 1 over R squared and the 1 over R terms go to 0. Brilliant. So we know out here, it's basically going to go to 0, okay? What does it go to as it goes to 0? As R goes to 0, what does this equation become? Is it positive or negative infinity? Which of those, both those terms are going to become infinite. 1 over 0 and 1 over 0 squared both become infinite, but which one's going to dominate? Which squared term dominates? Yeah, 1 over 0 is smaller than 1 over 0 squared, kind of thing. As 1 over 0.
It says 0 squared.
Yeah, 1 over put in a value of 0.1. Say put in a value of 0.1.
What is it, 0?
Exactly. Put in so whatever value, put in a value of 0.1, right? 0.1, 1 over 0.1 squared is 1 over 0.01, which is 100. 1 over 0.1 is just 10. So, and if you go to 0.000001, irrespective of what the L and the G are, you can make it so that the R squared term dominates because it's squared, right? It's always going to, eventually the R squared term will win, so that first term will always win. So this thing, as you go to 0, the 1 over R squared term will always be the biggest term, and that will actually become infinite. Okay, so we know if we go R is infinity, it's like that. Anything else? How else is it going to look? Is it going to cross the axis? What do we think it's going to look like? Is there a point where these things are equal? If there's a point where these things are equal, then that means there's a point where it crosses the energy is equal to 0 axis, doesn't it? Should we have a little look? So we could just solve this, right? We can just say, okay, well, if L squared over 2R squared is equal to GM over R, is there a question mark? Is there a point where that happens? In which case, that'll be where it crosses that axis, right? Basically saying energy is 0, this is equal to this, so so we can rearrange this. This is going to give us GM 2GMR is equal to L squared, rearranging, so R is equal to L squared over 2GM. That's just some number, right? L squared over 2GM, who cares what it is, but for any particular orbit with a particular angular momentum and a particular mass and a particular choice of gravitational constant, which is constant, so you can't choose that really, there's a value of R where those two energy terms are going to cancel it. So that it will cross the energy equals 0 axis at some point, right? Given by this particular thing. Yeah. That means at some point it's going to go there. So how's it going to fill in between? We know it's got to come down. But there's only one solution. This isn't R squared. It's not like it's going to go through that axis twice. It's just R equals this. It's going to cross that axis at one point. So R is that. And we know it's going to asymptote to infinity, but it's not going to cross there and then kind of yeah, and you'd end up with something like, that's not the greatest drawing of this because I've drawn it in bits, but it basically looks like this. It comes down, and you're right, if you differentiate it, there's a point here where the differential equals 0. So this effective potential looks a little bit like this. Okay, it's a good point. So here we've got derivative of the effective potential with respect to R is equal to 0. That's a really good point to start with, actually. So this is the effective potential, right? If I launched this with a total energy equal to this, right? So I set the system up. I've got my big mass m in the middle. I've got my little mass m. So I've got a certain angular momentum. I set it off with just enough speed that actually we are here. We've got just this amount of energy. What's going to be the motion of the system if I give it this much energy? the total energy is equal to this at this minimum, how will it be moving? Who said that? Circular orbit. Brilliant. Why is it circular orbit? Absolutely brilliant. Yeah, great. So you might think it's not moving at all, but remember this is just if its radius is changing. It's really good. So its radius isn't changing at this point, okay? But we know there must be some angular momentum. It's got some angular momentum. There is some L. So if you're at this point here, there's no force pushing it nearer or pushing it further away. So at that point, at that flat bed at the bottom of that effective potential curve, that's our circular. So right here, this is equals to circular orbit. Okay, so at that point it's a circular orbit. This is the radius, the circular radius, and it's got a certain energy it has at that point. Yes, sir. Yeah.
Either side of it, there will be elliptical.
Ah, brilliant. Yeah. Alright, we're doing this. This is awesome. So if you had slightly more energy than that, you're right. So let's have a little bit more. So this here, this is our circular orbital energy. Okay, so we have exactly that energy. dVdr is equal to 0. dVdr is actually the force. The derivative of the potential is the force, right? Again, it's showing that there's no force pulling it forward or backward, that there's only the centripetal force going to make it. So effectively it's not being accelerated towards the object or away from the object, it's moving in a circle. There's also, if you have a little bit more energy, if you're up here somewhere, alright, so this is energy circular. If you're here, actually it crosses that thing twice, right? So tell me, you're absolutely right. Why is that elliptical? You just felt it.
Because the angular momentum is changing,
Angular momentum not changing, right? Yeah, but you've got something right. More kinetic energy. Do anyone else want to have a go at explaining? You're absolutely right. Your intuition is spot on. We just got to work on the physics a little bit, but yeah. Okay. So for non-astronomers, remind us what those terms are. Okay, so this here we're closest, which is going to be. So this is perihelion here, and this here is aphelion here, isn't it? So that's as close as it can get for a given energy. That's as close as it can get to the smallest radius it can have, and the other extreme is the largest radius. So that's the aphelion of the orbit. Okay, and so and so if this is the total energy of the system, so this here is some energy elliptical, and so here we know the circular one here it has no kinetic energy in the radial direction. So it's kinetic energy. Its R isn't changing at all. What do we know about the system here and here? So its total energy is equal to the potential energy. So it also has no leftover energy for varying its radius. Okay, which means it's a turning point, right? So its radius has got as small as possible. Its radius isn't changing when it gets here. It's coming in. It stops when it gets to perihelion, and then it goes back out again. Okay, so at that turning point, there is no energy in the R dot is equal to 0. Yeah, it's a turning point. R is changing. So that kind of ties up. So here there's no radial kinetic energy. Here there's no radial kinetic energy. But here there's kind of a surplus, right? It has more energy than just the effective potential. And so that means in those positions there is some energy. Its radius is changing. Okay. So effectively it sloshes around in this potential from here. Perihelion comes out here. Aphelion back here. Perihelion back here. Aphelion. Okay. So that's an elliptical orbit. You can see it's bound. It can't escape. It can't run off to infinity because there's a lid at either side based on the overall energy. But it's letting it slosh between the two. The shape of this thing isn't symmetric. Okay, so this is not equal to the same as that. So it's actually slightly asymmetric, the shape of the the way the ellipse works. So the average position is actually going to move out. But it's exactly, this is an elliptical orbit given by this energy here. Brilliant. Absolutely brilliant. Oh no, we don't need to consider tidal forces. Probably somehow, I can't quite figure out how, but yeah, let me think. What if I increase the energy a bit more? What's the next interesting orbit that you get to? Where am I getting a parabola?
And the positive.
Nearly. Yeah, exactly. This one here, right? Equals 0. E equals 0 is parabolic. E equals 0 is parabolic, okay, so what does that mean though, right? It means that that's right. I mean, it comes in and it's got a closest approach. This is as close as it's going to get, okay, and it's going to whip around the mass, then it's going to disappear out again, and it's going to get slower and slower and slower and slower, and reach infinity at 0 speed, right? I mean, or whatever that means. Yeah, exactly. So this here is your parabolic orbit, and therefore, what do you get if you're above E equals 0? Hyperbolas. That's right. Yeah. So this is E is greater than 0. It's hyperbolic. And so for some particular energy here, this again is the position of closest approach, and again it comes in and it zooms out. But this one, when it reaches infinity, it still has some speed to it. It's still got velocity. Okay, so so the effective potential is only a function of radius. So if you remember, this graph is a function of radius, and it's for a fixed angular momentum. Okay, so we've said this is the angular momentum of the system, because during a particular trajectory that's fixed. So this
surely that it collides with the object rather than shoot up to an infinite.
Yeah, well, yeah. So I mean, if you just released it, you're right. If you got this close and just released it from 0, then the L term here would be 0, and all we'd have is the 1 over R, which would be a L equals 0 looks like that. If you just release it, it's always just going to fall towards it. But we've got this thing here, so maybe that's worth sketching on here, right? This thing here is basically our minus gm over r term, which is the gravitational attraction, the well that's always pulling them together again. But we've also got on there this term here, which is L squared over 2R squared, this one here, which is that basically comes from the conservation of angular momentum, okay? And when you get very close, that angular momentum wins, and so if you had an object that was infinitely dense, and you have a satellite, it's never ever going to crash into it, okay? If it's dense enough, angular momentum will always prevent it getting too close. It'll whip it away, and it'll zoom away, okay? So that's a consequence of the Newtonian potential system, yeah? Yeah.
If you were R equals 0,
yeah, but remember that these equations work outside the object. The Newtonian, this 1 over R here, is only if you're outside of the mass. Yeah, and if you're inside the Earth, I don't know, things like worms and rocks will get in the way of conserving your angular momentum. So this term is also going to mess up, right? So pesky worms and magma and all that kind of stuff, right? Which isn't very good for your angular momentum. So sorry. Well, yes, sort of.
like neutrinos.
Well, like neutrinos, yeah. So the main thing, right, which I think is quite nice, is that this little simple curve, the two terms in them, right, we actually can pull out the 4 different types of orbits just by considering different energy levels, right? And you can look at that graph and you can go, oh yeah, that's circular, elliptical, and you guys actually, with a little bit of cajoling, actually you saw the things in that graph, okay, which is quite, hopefully not too tricky, but it's maybe something you haven't seen before. I think this is a really easy way of explaining some of the Newtonian. We got that recorded as well. Yes, excellent. My new ringtone is you asking a question.
Is that even total energy?
E is the total energy.
Would it budge up and down though, depending on the r dot squared?
So the total energy is conserved, right? I mean, E is conserved. So you're saying at any point, if this is my elliptical thing, I've given it this much energy, say, my system. The only part of this curve it can exist is between here, because otherwise you've not got enough energy to access that part of the diagram.
Because you put the v vector equals that L squared.
Yeah, yeah.
We've like ignored that half.
Um,
You put the y equals the total energy.
That's right. So the excess. So if this is my total energy,
Yeah.
this is my potential energy. This difference here
Oh, okay.
is my kinetic energy. So it's how far I am above there. So if I'm right here, I'm a long way above there. So it's going to be the radius of kinetic energy is quite high at this point. Okay, I'm moving in or moving out quite quickly, and there's an extra radial kinetic energy used up there. Likewise, if you have this kinetic energy here, this is your closest approach, and then there's you've got bags of leftover energy, which is all about the object moving away from the sun, basically. Okay, so what was the last thing I wanted to do? Do you guys know that all these orbits can be described by these things called conic sections too? It's just kind of neat, right? So if you have a cone like this, right, as you take different slices through a cone, you get all these different shapes, right? Yeah, so it's nice, right? So okay. Did Christopher do the effective potential with you or not? Not that you remember. You remember the conic sections. You don't remember the effective potential.
We did that. We looked at the
Kirchhoff's laws.
I can't remember.
Kepler's.
Kepler.
Kirchhoff's conservation of charge. You're like, the junction, Okay. I like this, particularly what we're going to have a go at next. So just to reassure you, right, so in the notes I have some stuff here about how you can, from this equation you can rearrange and you can mathematically get the elliptical orbits and the parabolic orbits and the hyperbolic orbits. It's a little, you have to change, you basically take this equation and you change from using r to using 1 over r as your coordinate. It makes it a bit easier. You end up with an equation like this thing here, which is called Binet's equation, and that ends up just as this factor of E, the eccentricity. You end up getting the 4 different types of equation that we've seen. From here you can't actually tell that this one here is elliptical. We had to bring other knowledge in, but we know for sure that this is bound. We know it has a minimum and a maximum radius, but from this graph alone we don't know actually that it's elliptical. Okay, you need to do a little bit more maths to prove that, but you can learn quite a lot about the orbits from this. Okay, so imagine, like, kind of looking from above, you can imagine you can draw here's your mass, and there would be some, for a given energy, you can say, okay, well here's a circular orbit here. For a higher energy, you've got a minimum. This is awful. You've got a minimum radius there, and a maximum radius there.
Does that make it easier?
I don't know. I'll just be rubbing it out the whole time. You guys have imagination. So there you go, that's not too bad. So there's my central mass. This is maybe the minimum one, this is the maximum one, and so for a given energy, this elliptical one, it can get no closer than this, it can get no further away than this, so maybe this is the R minimum, this is the R maximum corresponding to here, and whatever the planet does, it's got to kind of do something in between those, right? You don't know quite what it's doing, but you don't know. Here's the minimum, here's the maximum, and it can't go closer than the minimum, it can't go further than the maximum. It's somehow stuck between them. Should I just then scribble over that as well? Yeah, my kids can draw better than this, I know. It's video, so you can see the development, you see. So yeah, it's not just the scribble, it's the route to the scribble that's important. Alright, we'll maybe stop there for a second. Alright.